Okay, guys, we're going to move on to the final chapter here. This means to say that once we're done with the final chapter, it will be another chapter, guys. And hopefully this time, everyone does better than the previous time. Of course, you will be definitely rewarded if you do well. You will be slightly punished if you do not do so well. Slightly. And when I say slightly, you just have to suffer some verbal abuse. Okay. Anyways, moving on to this last chapter of thermal physics. It is basically thermal conduction, guys, thermal processes or thermal transference, right? In your syllabus, there are three main ways that heat can be transferred. The first one is obviously conduction, the second one is convection, and the third one is known as radiation here. Oh wait, am I should be? Okay, so anyways, in order to understand conduction, convection, and also radiation, let's imagine today we go for a little class trip, a little camping trip somewhere. Okay, let's imagine, guys, today when you go camping, as soon as you reach the campsite, obviously the first thing you're going to do is you're going to start up a campfire, right? So let's say you have a campfire here. Poorly illustrated. Actually, it's quite nicely illustrated, I would say. A nicely illustrated campfire here. You knew I had an art for drawing. I had a knack for drawing. I'm not doing well. Okay, but anyways, when you reach this campfire here, let's say, for example, friend A, let's just say friend A is an idiot, right? But he's hungry. He's an idiot, but he's hungry. So what he does is, right, he takes a metal stick. Oh, forgot to draw his head. He's not that headless henchman. Right. So let's say he's an idiot. So he takes a metal stick and then he uses it to roast marshmallows onto it. Okay? Idiot number one. Uno. And then friend number two here, he's not an idiot, but he's a little bit cold-hearted. Let's say this friend is a girl for diversity's sake, right? This girl is a bit cold-hearted, so usually what she does is she's a bit afraid of the cold, and thus she puts her overly long extended hands above the fire, right? A little bit like the Slender Man. Okay, and the third guy here, he's a bum, right? So when he reaches the campsite, he says, "I'm really tired already. I want to just go sleep." And when he sleeps in his beanbag. His sleeping bag, sorry. Oh, oops. That conveniently is drawn to look like shit. But it's a sleeping bag. Okay, he sleeps right beside the fire. Michelin Man. Yeah, the Michelin Man. He's not dead, by the way. He's just way sound asleep. Okay, anyways, all these three guys here, they are definitely going to get some form of heat transference. Let's start with idiot number one here. What do you think this guy, how is this guy getting heat from? Conduction. Conduction, very good. So how does he get conduction? Guys, if you think about it, right, conduction in a very simple manner, right, is basically a conducting heat from one thing to another. And since this idiot here, wait, drawing, stop drawing on the thing, pay attention. What are you doing? Well, I know you're definitely not paying attention. Listen to this. Hey, listen up, So since this guy is an idiot here, right? What happens is as the heat is as this heat is heating this marshmallow here, the heat kind of transfers through this metal bar and eventually burn your hand, right? You know, if you've ever seen someone dumb before, they'll touch something really hot so it was real life experience.
Camp experiment. We had to heat up this thing, this little spoon that had a piece of metal in it. You're supposed to put it into oxygen to see reaction. My dumbass went against the spoon right after we put it up.
Nice. So that's your first hand experience. That is essentially conduction, guys. For conduction to occur, usually it requires one thing, which is usually the third party object. Okay, in this scenario here, the third party object is obviously going to be the metal rod here, right? And conduction only occurs in two specific mediums. It will either conduct through solids or it will be conducted through liquids, guys. Very important. Conduction only occurs in solids and liquids. That's why when you heat up water, you're actually conducting heat to the water layers above, right? Right. So very important. This is the first thing. And usually conduction, if it is a conductor, right? For example, metals, it involves free moving electrons. Very important. Why is this very important? Because they always ask this in your exam. Whenever you identify the word that it is conduction and it is a metal, usually it's free moving electrons. Which a lot of students they tell me, hey, isn't free moving electrons responsible for conducting electricity instead? The answer is yes. Electrons not only conduct heat, they also conduct electricity also. So that is why metals generally can conduct electricity and conduct heat very fast. Okay, so this is the first key things that you should know. How about person number 2 here? The diversity sick person here. What? Convection, very good. Why is it convection here? Now, guys, convection has a very, very important key characteristics. Convection basically states that heat will always travel upwards. That's why if you ever play with fire like last week, right, you'll notice that actually, if you put your hands above the fire, you will feel the most amount of heat. But if you place it next to it, you still feel some heat, right? But not as much as you place your hands above the fire. Okay, very important. So convection states that heat travels upwards. And which mediums do you think convection occurs in? Liquid and gases, guys. Convection can only occur in liquid and gases here. Okay, very, very important. So this is the first 2 key characteristics here. And finally, this last bump here, obviously he's getting heat through radiation, right? Radiation, good. Why radiation? Now, radiation is the most special among all these forms of all these forms of heat transference. Radiation is the only heat that travels in all directions. Travels in all directions. And does radiation require a medium? No. Why not? Radiation is the only one that can travel in vacuum. Shit. And how do I know that radiation is the only one that can travel in vacuum? The very simple example is when you're in the, not when you're in, like the sun transferring heat to the earth, right? If you imagine the sun being the middle of the solar system, right? Contrary to much belief, you are not the center of the universe. But anyways, let's imagine here is Earth, and Earth. I mean, there's no 4 Earths. It's like moving Earth in different positions here, guys. We know for a fact that Earth moves around the sun, and regardless of wherever position the Earth is relative to the sun, the heat will still be able to transfer, right? And in between these spaces here, this is essentially what we call a vacuum, right, guys? For those who do not know, a vacuum by definition is a place that has no air molecules. In other words, vacuum is just a fancy term for space. Okay, sorry, space is a vacuum, but we can recreate a vacuum on Earth also. Remember the first video that I showed you guys, the one where they sucked out all the air molecules in the spot, right? Remember, that is basically a vacuum. A vacuum is basically by definition somewhere where there's no air molecules inside. That is why when you shout in outer space, usually no one can hear you because sound requires air molecule vibration for it to transfer, right? So remember. Okay. So anyone has any questions with regards to this part here before? Good, 100% absorption rate. Absolutely what I love, right? So if you look at this diagram here, right, this is just a very simple, another simple form of how conduction, convection, and radiation is different. Conduction is when you're an idiot, right, and you touch the metal spot, right, and then you touch the metal spot here, then obviously heat will be transferred, right? This is conduction. Convection occurs in liquid and gases. Guys, in fact, if you ever notice on the highway before, like, have you ever like watch far into the highway, right? You notice that like there's some steam coming up from the ground. Have you guys ever noticed that? You know what's actually happening? When you see the steam coming up from the ground, is because the tar road is actually heating up the air molecules above it. I repeat, the tar roads are heating up the air molecules above it, causing convection to rise, heat up the air molecules and go towards the top. Guys, next time, try to pay attention. If you're on a hot day, then you see like very, very far away, right? You see like there's some gas steams coming up. That's usually going to go. Hey, move this table closer towards the middle here, so then you don't have to like keep moving every time. Move this table closer to the thing. Very, very good. Okay, guys, then radiation is the most interesting one. Irradiation basically states that heat can travel in all different directions. It can travel in all different directions and it can travel in the back. Okay, so having said that, let's go more detail about conduction, convection, and also radiation. If you look about this in terms of conduction, guys, conduction is a transference of heat in solids, usually involving third-party objects. Guys, don't copy first, pay attention first, right? Different materials definitely have different conductivity, right? For example, metals are generally better conductors of heat, right? Good conductors are things such as metals, as heat is easily conducted. Bad conductors are known as insulators. What are the examples of insulators? Rubber, glass, wool, plastic. All these things are known as insulators. Even sand also, guys. They are insulators because they do not conduct heat or electricity. Right? Heat is not easily conducted in them. Examples of good conductors and insulators include the following. Okay, can you guys copy everything now? Okay. But Justin go. Oh yeah, let me check the computer first. Where were you, by the way, last week? Tolerances. I'll let you know when we play with the final experiment again, okay? I'll make sure to include you. Okay, anyways, everyone. Okay, Alright, hurry up, Justin. Okay, so if you look at this simple this next page here, this is basically a simple experiment to test out which is a good conductor and which is a bad conductor. The experiment is very, very simple. Basically, you have 4 different metals made of obviously different materials: iron, copper, brass, and aluminium. All 4 of these metal rods they are cased with something known as Vaseline. Vaseline is just like a kind of waxy material that melts when it's heated. And on the other end of the Vaseline, you basically stick a drawing pin here. So what happens is, right, you place all 4 metal bars and you heat it together under the same heating source, right? This will cause the heat to transfer all the way to the end here, melt the Vaseline and drop the drawing pin here, right? Obviously, the concept here is very simple, is that whichever one drops the pin the fastest is the best or worst conductor. It's the best conductor, right? Whichever one drops the pin the fastest, that is essentially going to be the best conductor of heat. Okay, so if you look at this time here, this basically says that copper is the best conductor lah, because it dropped the fastest, and steel is the worst conductor, even though they are all metals, but different metals will have different conductivity, right? And because of that, you'll see that steel is actually the worst conductor among all of them. Okay, now in your exam, usually if they ask about conductivity, guys, conduction or whatever, right? Usually they'll ask you to state how it happens in a molecular level. Okay, and in a molecular level, you look at this diagram here, this basically gives you a simple explanation. Imagine today I have a heating source here. This is a metal bar, by the way. If let's say this is a metal bar here and I have a heating source here, right? What happens is, right, if this end of the metal bar is heated, now obviously this particle is going to gain the most energy initially, right? And when they gain energy, what happens is they start vibrating. They vibrate, and they pass on energy to the adjacent molecule. Energy vibrate, pass on energy, vibrate, pass energy, vibrate, pass energy, vibrate, pass energy, vibrate, and pass energy, vibrate. That is why heat always conducts from the hot end to the cold end. It's because it takes time for the molecules to vibrate and then pass energy to the colder region. Okay, so this part here is supposed to explain how conduction occurs, guys. All right, so if you look at the statements here, as the bar is heated, the particles gain energy and vibrate more, right? Lattice vibration. What is lattice vibration again? What does lattice vibration mean?
Structure, structure.
Yeah, you're somewhat right, but the more exact term is they vibrate at fixed positions. This is what they call lattice vibration, right? Occurs, right? And then the free movement of the delocalized electron pass on energy. This is a key word here. I see this come up more and more in your paper 2 these days. So you better know that the conduction is because of the delocalized free moving electrons. Right. Then thermal energy transfers from the hot end to the cold end as the particles pass on their increased kinetic energy to the particles along the bar. Like I said, they vibrate, pass energy, vibrate, pass energy, and so on. Liquids definitely have weaker intermolecular forces and more space between the particles, which makes the vibration of the particles harder. Right, this is the reason why last week we keep saying that specific heat capacity of water is relatively higher. It's much harder to make them pass on energy because the molecules are relatively further apart. Unlike solid particles, where the particles are already close together, if I vibrate, this one is going bound to vibrate together also, right? Because they are already touching already. Okay, gas definitely have more space in between them and therefore infrequent particle collision. This makes liquid and gas poor conductors of heat, guys. The only reason, one of the reasons why conductors or metals generally have low specific capacity is also because the molecules are very close together. It's easy to vibrate and pass on energy along. Okay, everyone? Anyone don't understand this? This is important. You'll see this in your paper too. Yes.
What?
It's like, anyone don't understand this? Okay. Anyways, this next part here is equally as important. I see this come up once in a while in your paper 4 or paper 2 as well, guys. This one here is basically explaining how convection current occurs. Have you guys ever heard of convection current? No? Never? Okay, let me give you a very simple, relatable scenario. Guys, if you ever cook Maggi mee before, right? Anyone here never cooked Maggi mee before? Because they have either food consciousness or they have a very well privileged life for a kakak to help you cook for it. Right? If you ever cook Maggi mee before, go home and try to do this for the sake of understanding, right? Let's imagine this is water, and then let's imagine I heat it up in the middle here. If you ever cook Maggi mee before, you'll notice that, right, as soon as the water starts boiling, the bubbles actually go towards the side of the pan. Have you guys, anyone ever cooked Maggi mee before on your own? Have you ever noticed this before? The bubbles kind of go towards the side of the pan. You know what's going on inside the water? Something known as convection current occurs. Let's imagine today we split the water in half here. Okay, if we split the water in half, we only focus on two particles. One particle that is closer towards the heat source, and another particle that is relatively further away from the heat source. Okay, so what happens is, right, if you think back in terms of last 2 weeks classes, guys, we said that heat causes the particle to do what and cold causes the particle to do what again? Chapter 2.2, the first thing I talked about, what was it? Good. Heat expands and cold contracts now, right? If you hold on to the idea that heat expands and cold contracts, right, then you can kind of understand what's going on here. Today, these particles are relatively closer to the heat source, right? And when I heat it up, obviously these particles will expand just slightly a little bit more. Okay. Now, according to your density formula, what's the formula for density again? Good. It's mass over volume. Today, if I heat up these particles here, will the mass change? Will the mass change or not if I heat up the particle? Will it change? Yes or no? If I heat up any particle, will the mass change? Good. Yes or no? No, it will not. Why won't it change? Because no matter how you heat up that one particle, unless you evaporate it, right? Unless you disintegrate it, right? If not, the mass will not change, right? You know when will the mass change? If let's say you have a piece of paper, right, and you burn it, you're disintegrating the whole paper, right? You're burning up the whole paper, then the mass is going to change. But this water particle, if I heat it up, it's not going to change unless you heat it up to very extreme ends, right? And maybe you can cause it to change to gas. But the mass is still conserved, right? So first things first is you need to understand that the mass will not change. And when the mass doesn't change, an increase in volume will cause the density to... What happens to density when the volume increases without changing the mass? Good, the density is going to decrease, right? And when the density decreases, this will cause the hot particle to what, guys? What would happen when the density decreases? Good, it will float upwards. Guys, whenever you see the word floating upwards or sinking or density, you must interrelate all three things together. Density causes objects to float or sink, either one only, right? So when these hot particles, they rise towards the top, then obviously what's going to happen is it's not going to leave an empty space at the bottom, right? The relatively colder particles is going to go to the bottom, right? And then the whole cycle is going to repeat again. Right now, these particles are closer to the heat source, so they're heated up, then their density decrease, and then go up, down, up, down, up, down, up, down, up, down, up, down. This is essentially what we call convection current, guys. This is essentially what we call convection. Okay, the up and down of heat, hot and cold particles. And guys, let me clarify out when I say hot and cold particles, I'm not saying like, oh, you know, this hot particle is 100 degrees Celsius and this cold particle is 50 degrees Celsius. No, definitely not. What do I mean when I say relatively hotter and relatively colder? Maybe this one here is at 99 degrees Celsius, right? This one here is at 98.5 degrees Celsius. Right, because it's impossible to have two different temperatures in one object, right? Thermal equilibrium will eventually take place, right? So it's impossible, guys, it's impossible. It's relatively colder and relatively hotter only. Okay, very important. Anyone don't understand this concept? Very important. In your exam, they'll ask you this. You know how they ask you? They say that, oh, explain in terms of molecules or explain in terms of density how convection current occurs. And you're supposed to say that the hotter particles receive heat energy, which causes their volume to... Which causes their volume to do what, Chong-Yi? Dosing off there. What will happen to the volume when they're heated? The volume will increase. This will cause their density to what? Decrease, causing them to float towards the top, the colder particles replacing them, and the whole cycle repeats again. Okay? So if you look at my statements here, convection is a don't copy first, pay attention to what I have to say. Convection is the transference of heat energy in liquid and gases. When liquid is heated, its volume will expand and thus density will decrease. Right. Water above the heat source becomes warmer, expand, and rises as it becomes less dense. The cooler, more dense water sinks to the bottom of the beaker and once again is heated. Right. Then the circulation of warm and cold water sets up a circulating stream known as convection current. Now, convection current doesn't just happen in your magnetic pot, guys. You'll notice that even the Earth's core is causing convection current, but at a much more slower pace. You all know about tectonic movement, right? Everyone knows about tectonic movement, right? Tectonic movement didn't just say like, oh, it's time to move to a different place, and then they shifted to a different continent. Tectonic movement is because the core is hot, right? Causing the mantle here, which is half liquid, half solid, right? To kind of go through convection current. Very slowly, it will move it towards the top, and very slowly, the tectonic plates will eventually move up. So this is something that is in a much larger scale of convection current. But if not, then most likely it's going to be the magnetic pot story, right? The water go up, and that water go up, go up. So if you put two wooden blocks here, they'll actually go towards the side of the pan. Okay, ladies and gentlemen, anyone has any questions they want to ask for this part here? What's up with you today?
What?
Why are you acting weird?
What do you mean?
Okay, copy everything down. Once again, thank you for the contribution of the growth of efficiency. Share to succeed. Here's your dividends. Okay, guys. Last but not least. Oh, yeah. Okay, but last but not least, we go to the final part here, which is radiation. Now, guys, in your exam, I've noticed whenever they want to test your understanding on radiation, right, they usually ask about the black, white, and silver colors one. You guys know about the black, white, and silver colors, right? I think you guys learned this for sure before, right, in year 9. Stop. Okay. Okay, let's imagine this story here. Today you want to go onto a beach. Right, here, that's right. Okay, let's imagine today you want to go to the beach, right? Right. Let's say it's a sunny day today. Oh, what a wonderful day to go to the beach. You being a science student, right? You'll notice that hey, it's really hot. So when you choose your clothes to wear to the beach, what color will you choose? Huh? What color? White. You wear white in color. Right? It's white. And then you're happy with a very long neck. Your girl. Okay. And with very short hands. And legs. But anyways, you're a science student, that's why you wear white in color. Right. Then one of your idiot friends, right? Maybe he's from the business stream or the art stream or whatever it is. Discrimination. Just joking. But no doubt he's an idiot, right? So he decides to wear black color to the beach. What happens when he wears black color to the beach? What happens when he wears black color to the beach? Oh, I don't know. He absorbs more heat. Excellent. Very good.
Like Superman, so like
Like Superman, he absorbs radiation, but unlike Superman, he will not do anything else. Right. So what happens is, right, basically, we know for a fact that white is definitely more cooling and black is more hot. Why? Because from here, first things first is you need to understand that black is actually the best absorber of heat. Best absorber of heat. And because they are the best absorbers of heat, they are also known as the best emitters of heat. You know what does emission mean? You know what does emission mean? It basically means that if I absorb the heat to my t-shirt already, right, I can emit it back into my body, you know. So if you were to like very simplistically look at the trail of the heat, right, the heat is being absorbed, most of them absorbed here, and then the heat is being emitted back into your body here. Right. So that's why he'll feel hot like crazy, for sure. For like when I say hot like crazy, don't like damn hot. Once again, this guy is not going to go through 100 degrees Celsius and this guy is not 26 degrees Celsius. No. Once again, maybe the difference is a little bit more or less only. Let's say, for example, if this guy here, right, is experiencing 40 degrees heat, this guy probably experiencing 38 degrees heat, which is more than enough, right? Because our body, you know, right, 1 degree off the normal temperature, you're already fever already. That's why even though it may seem like the number is very small, but a few degrees difference will make you feel hot like crazy already, because essentially you're going through fever already, something like that. Okay, so white, however, is the best reflector of heat, right? So because it's the best reflector of heat, it has very little to be emitted back into you also, right? White is always the best reflector. Recently, I had one student that asked me, right, up until that day, I also didn't really think about it, but why is white the best reflector of heat? Why is black the best absorber of heat? Why? God has favorites. I'm just joking. Shut up, lah, you. Why does white reflect the most heat? And if you think about it, right, do you know how colors work?
Black, essentially, white is like every single color makes it work.
Good, very good. Have you guys ever seen this experiment before? Have you guys ever played with the 7-color spinning ball thing before? No one. Okay, good. Let me enlighten your world once again. I'll play some fun or some Dota and Impact. 7-color spinning color, like it's called. I always don't know what's this thing, but have you guys ever done this? Have you guys ever done this in school before? Have you guys ever done something like this before in kindergarten or in primary school? You have one cardboard that is made of 7 different colors. Do you know the concept here, right? You know, like the sun's light. You're going to learn about this later on in the wave chapter as well, guys, because light is a form of wave, right? You know the sun actually emits white light, right? Do you know that white light is a combination of 7 colors? You guys know, everyone knows this, right? So do you know that the 7 colors, if you combine it fast enough, it'll turn back into white light? Okay. Have you guys tried this experiment before? So the whole experiment is very simple. Basically, you just color one circular block into 7 different colors. You tie some strings into it, right? And then I can watch the video at home later on, but essentially this is the important part. You see this? The 7 colors, if they go fast enough, I mean, this is not a good one, but if you go fast enough, they'll eventually turn back into white color again. Right. So if you think about the concept of why white is the better reflector of heat and why black is the better absorber of heat, let me give you a very simple example first. Let's imagine today, right? You have a blue color box here. Okay. Let's say you have a blue color box. Okay. You know why it's blue, right? Do you know why it's blue? It's because when the sunlight, I mean, I can't draw white color of course. But let's imagine this is the sunlight, which is white in color, by the way. I just don't have white color here. Okay. When sunlight hits this thing, Sunlight has 7 different colors, red, orange, yellow, green, blue, indigo, and violet, right? This blue color, right, it actually absorbs everything already, you know. It absorbs red, orange, yellow, green, reflects blue, then absorbs indigo and violet also. So that's why when it reflects to our eyes here, we can only see this color here, blue in color, right? So if you think about why black is the best absorber of heat, right? It's because essentially, shit, why my box draws so ugly, whatever, right? Essentially, if there's black color here, right? What's happening here is, right, when the light hits this black color here, all the colors is absorbed, right? Red, orange, yellow, green, blue, indigo, violet, right? All of it was absorbed already, and essentially almost nothing reflects back to our eye. That's why we see black in color, right? And if you think back right now, the concept of white, let's imagine this is white, guys. No white color once again. Shit, the box is getting uglier and uglier. But essentially, this is white, right? You know what's happening here when the white light hits, right? Red, orange, yellow, green, blue, indigo, violet, right? All is reflected back into our eyes. That is why this concept here, right, explains why black is actually the best absorber of heat and white is the best reflector of heat because they reflect all 7 colors back already. You get what I mean, guys? This is the reason why. Okay. Interesting, isn't it? I didn't really think about it until that day my student asked me why. Yeah, why? Okay, so from here, first and foremost, the information you need to know is that radiation is the transference of heat through light, right? When light is emitted, it's due to the presence of infrared, guys. Guys, you know when you put your hand up into the sun, you can see it and you can feel hot. It's due to 2 different things. You can see the sunlight is because there's a visible light there. And then you can feel the heat is because there's infrared. Every time you see this word infrared, which is always tested in your exam, you need to know it's everything related to hot. Whatever that is hot, right, is because there is infrared radiation in it. Okay, and then the sunlight also emits one more form of ray. There's visible light, infrared, and who can tell me the third one? There's one more. Good. There's UV light there. UV is the reason why people get skin cancer when they do too much skin tanning. You know, like a lot of Americans, they're damn dumb one. I mean, yeah, they're dumb, right? Anyways, you know when they go for summer holidays, they go on sun tanning for 5 hours straight in a row, from mornings tan all the way until night time. And even if there's no sun, right, they'll go to these stupid things known as the tanning saloons. If you guys watch enough American series, you know, like they go for the tanning saloons for the tan, right? It's actually not that good, like too much of something will never be good, and when you're obsessed with your tan, right, usually they keep going and going and going. You'll have a very high possibility of getting skin cancer. That's why if you put sunscreen on, like your sunblock and everything, usually it's block the UV light, not the visible light or ultraviolet. You'll still feel hot. You'll still see the sunlight, right? So UV is the one that causes skin cancer, but infrared is the one that causes the heat. Okay. Light and infrared is part of the electromagnetic spectrum. All electromagnetic waves do not require a medium, meaning to say radiation, which is heat, is the only one that can travel through space. Okay. Right, and then this part here, emitters are basically those that give off thermal energy, absorbers are those that take. Okay, this one you must know. Always ask. In fact, for sure come out in the exam. It's quite straightforward. I think like it's not rocket science, right? Silver is the best reflector and black is the best absorber. And because black is the best absorber of heat, it also emits heat the most. It's the best emitter also. Okay? And then, yeah, this is a very simple experiment to test out whether black is the best absorber of heat. So the whole experiment will go something like you're going to pour hot water into a block that has all 3 different surfaces, black, white, and silver. And you take a thermal gun to measure the temperatures, right? Which one do you think is the hottest? Which one is the hottest among these 3 surfaces? Yeah. Because it absorbs the heat from the hot water and it emits it upwards, the best one. Silver actually will be the coolest because it reflects most of the heat back, right, and it cannot emit as much heat anymore. Right? You get what I mean? Okay, so this is that. And final thing that we talk about before we go into the exercises today is thermal equilibrium. If you ever held your boyfriend or girlfriend's hand before, right? One of you is bound to feel hotter and one of you is bound to feel cooler. Why? Because there is a net transference of energy. If you, let's not talk about boyfriend and girlfriend. Let's say, for example, if you put your hand on some metal railings on a cold day, you feel that the metal railing is really cold, right? If it's really cold, it's because your hand, which is hot, is constantly transferring energy to the colder spot. And this thing is transferring energy also, but much less impact. That's why you feel the cold sensation, right? But if you hold onto the metal rail long enough, eventually you won't feel hot or cold anymore. It's because the amount of energy that you give is the amount of energy you receive already, guys. This is what we call thermal equilibrium. Thermal equilibrium basically states that there is no net transference of heat energy. Okay. So an object is at constant temperature when the amount of energy received is the amount of energy transferred. Okay, guys, anyone's got any questions with this part here? Anyone? All you sleepyheads today? What were you guys doing last night? Okay, yeah, if you have no questions, nothing to copy yet. Okay, start attempting the questions at the bottom here.
Think the results that you may expect, we don't do it often, black or white. Yeah, that's how we do it. So you see, that's.
Yeah, I see like the piece.
Okay, well, this one here, right, you're supposed to actually tell them how the experiment. Stuff. Right, you're going to measure the initial temperature, then after a certain time, you're going to measure all three temperatures from the size. That's how we're going to understand the experiments. It's something good change on role. Okay,
Yeah, of course. Chinese, you say usually black heat and this black reflector is the most emittent.
that's all.
You think about, the nice green screen thing, it's easily because it's not reflected on the green screen.
So.
Sorry?
Chinese is.
Yeah, for sure. Hey, I want to talk about this thing which I see a lot of kids doing these days. You know the prank where you sit down and then your friend pulls the chair away and then you fall to the ground, right? You know what happened? You know people will fracture their limbs and they'll lose their ability to walk on, you know. So if you ever see any of your friends doing that dumb prank, I mean, you better tell them it's not funny, man. People will actually lose their ability to walk. Right now I saw a news, right? Some kid was pulling that stupid prank while the girl was sitting down. Now she's traumatized, not just traumatized, her legs cannot function anymore. She'll be wheelchair bounded for the rest of her life. I see this a lot in the high school setup, guys. If you see any of your friends doing that, make sure you voice it out because you never know who's going to be wheelchair bounded next. We're talking about this kid. Yeah. Bro. It's like it's still it's really bad. In fact, I've heard about this problem since my days in students. Oh, sorry, I thought it was big. Okay, else. So So actually, oh, can we discuss some of the answers before we proceed on? Starting off with this patient. My God, she's not here. Hmm. Hmm. Okay. Anyways, if you look at this question here, guys, I think some of you guys may be stuck with this question or you may not know how to do this. They ask you to describe how you would use apparatus to compare the abilities of the two surfaces to absorb infrared radiation. So you are actually supposed to describe what you're going to do with these things here to compare the abilities to absorb infrared radiation. Right? So you're teaching them what to do, you know. So if you look at this answer here, it's actually very straightforward. It says that they ask you to heat the same time and take temperatures of both both thermometers. So of course you're going to structure it nicer, lah, right? You're going to say something like, place the Bunsen burner equal distance from both surfaces heat at the same time. Why must it be equal distances? Because you can't be one closer to the other. After a certain amount of time, measure, if I record for both thermometers. Something like this. Okay, then obviously state the results you will expect. Which one will have the higher temperature? Definitely the something like this. And it will be the same for the next question also, but instead of 2 marks, it will be 3 marks, guys. Instead of 2 marks, it's going to be 3 marks. Okay, everyone okay with the first one? Okay, if you look at the next question here, it will be exactly the same thing, but instead it will 3 marks. But this time here, they have a supply of very hot water. So this extra marks here is you have to pour the hot water into the water inlet. Alright. So describe how we will use this apparatus to compare the infrared radiation from the 4 surfaces. Once again, yeah, I would fill the water in first. I'm gonna say something like something along these lines. It doesn't have to be word by word, guys, but you need to know what you're doing. Hey, you kick football with your Ziyang, is it? You kick football with him, is it? Ziyang, Ziyang. Oh, I think you kick football also, and he kicks football, but they don't kick together. Different class, is it? Because yeah. And you used to kick, but now you're a basketball player. Okay. Okay, then obviously suggest which surface is the best emitter. It's obviously going to be the black. The worst one is obviously going to be the silver. Okay. Yeah, the rest of it, please do it as homework, guys. We'll continue the answers next week. This ABC one, I think you should be able to complete everything, guys. Please make sure you do until this page here. Guys, what we're gonna do next week is that we're most likely gonna finish discussion on this paper. We'll do a little bit revision on the whole thermal physics, and then the week after that, which is your holiday week, we're going to have a thermal test. Okay? On this day, the whole week, then you'll be 9. Wow, it means to say you'll miss 2. You're gonna miss 2 classes. What the hell? 去哪里？日本 Australia? So choice. Oh yeah, but anyways, there's gonna be a test here. You miss the test. But try to do it one way or another. See how? Most likely the first we're gonna have a test. The first we're gonna have a test. Then this week is you guys' holiday, right? Are you having holiday also this week? April? Like April, this one here. You're having holiday also, right? Okay. Okay, guys, that's gonna be it for today. I'll see you all next week.
Bye bye, Emma.
Guess who just got invited to a free movie?
Yeah, yeah.
That's all.